All right, hi guys, welcome back. We're going to be talking about gases. This is chapter 11 in your textbook in case you want to use that as well. Again, get out a piece of paper because there will be 2 U-tries in this video. And I think having that out will be beneficial for you. If at the end of this you still have questions, you can let me know and we can talk. All right. So we are starting properties of gases and gas laws. So the first thing that is important to understand is the kinetic molecular theory, or it'll more commonly be referred to as the KMT. And this is just a way or a model, I guess, for understanding how gases behave. And there's 4 sort of big ideas here. 1, a gas is a collection of particles, and particles are molecules or atoms. It's an interchangeable term here, but we'll go with particles for now, in a constant straight line motion. So essentially, those particles are always going to be moving in the same uniform way. And the second idea is that gas particles don't actually repel each other. They don't interact at all. They may collide with each other as in a form of chance, or they may collide with surfaces around them in a form of chance, but they always just bounce off each other. There's no interaction. There's no binding together. They just sort of bounce around. And the common example that's always used is if you've ever played pool before, and if you've ever used a pool cue to hit one of those pool balls, and you'll watch them bounce off the sides and bounce off each other, but essentially they all act independently. The next big idea is there's a lot of space between gas particles compared with the size of the particles themselves. With this, because there's so much space around them and they're relatively small in size, it gives them the ability to be compressible or have a high compressibility. And that's another property of gases that we'll go over. And for the average kinetic energy, and that's kinetic energy is energy due to motion, remember, of gas particles is always proportional to the temperature of gas in kelvins. So the energy of the gas is proportional to how warm or cold the temperature of the gas is. So essentially, if temperature increases, then the particles will move faster and therefore have more energy. If the temperature decreases, the particles are going to move slower and they'll have less energy behind them. Makes sense. So what are the 3 properties of gases? And these are actually things we've already covered, but the kinetic molecular theory will support these 3 properties. So gases are compressible, and if we go back to the KMT slide, that is due to that space, that relative space that exists in comparison to the size of gas particles. And then 2, to assume the shape and volume of their container. With this, the fact that they act like those pool balls, and they're able to fill all of the space that's around them. They'll keep actively moving in that straight line and fill the space around them. And then 3, have low densities in comparison with liquids and solids. So again, this gives them their compressibility. Okay, so the result of the constant collisions between atoms and molecules in a gas and the surface around them, that's what defines pressure. We have to understand pressure if we're going to understand how gases interact with each other and interact with their surroundings. And pressure is defined as force over area. So the way pressure works, you've probably experienced pressure a lot in your lifetime. You've probably experienced a change in pressure as you go up in an airplane into the sky. The pressure is much lower up higher in the air because there's less air, and there's less molecules, there's less particles of gas in the air, so the pressure decreases as you go up. So your ears will start to feel weird as you go up into the airplane. They may feel like they're very full. A lot of people describe it as like they feel like they need to pop. That is your ears trying to equalize. Now, what's interesting actually is most airplane cabins, where at the place where you sit, have they equalize the cabin pressure, so it's not as drastic when you're flying up into the sky. Now, the fewer gas particles that are in the air, the lower the pressure. This makes sense. So if I have 2 containers and I fill one with a bunch, the pressure inside is going to build. If I have less of them, there's less interactions happening, there's less pressure. We also have to understand pressure units. So pressure is measured in 3 ways: ATMs, PAs, and mmHgs. That's atmospheres, pascals, and millimeters of mercury. Atmospheres is the average pressure at sea level. A pascal refers to Newton, 1 Newton per square meter. This is the SI unit. And then a millimeter of mercury comes from mercury barometers, and barometers measure pressure. And if you actually remember, you guys don't remember, we had a great mercury spill of 2019 in our science building, and it was due to a mercury barometer dropping. And by the way, in your Canvas page, there's going to be a unit conversion reference sheet and a equation reference sheet. For this unit, you will need to have that. So it's in your Canvas page. I would download it and save it to your desktop so you can access it. And if you do have access to a printer, it would be really helpful to print that out. So you can find that in Canvas. Okay, so we're going to talk about 2 gas laws today. There are 5 that we're going to learn in total, but we're going to learn just 2 today. The first one is Boyle's law. And Boyle's law talks about the interaction between pressure and volume. So if temperature and the amount of gas are constant, so temperature of the gas and the quantity of gas are constant, then the volume of the gas and its pressure are inversely proportional. This makes sense. So if volume increases, the pressure decreases. If volume decreases, then the pressure increases. What does this look like? So imagine I have 2 cylinders, and imagine I have the ability to make that cylinder's volume smaller or larger. So in this case, instead of filling up the whole cylinder, I've capped it. I have pushed down I have a movable piston perhaps, and as the volume of the cylinder decreases, I only have some of the volume accessible, then the pressure is going to increase. Because remember, if temperature and quantity of gas are going to remain the same, the temperature is the same in this one as it is in this one, the quantity of gas particles, if you were to count these, are identical, then the only thing that's changed is volume. And as a result of having a smaller space for these particles to interact, you're increasing pressure. Same thing here. So we have more volume available. Remember, the pressure and the quantity of gas are the exact same, but I have more space available for particles to interact, so my pressure is going to decrease. That's what Boyle's law says. Now, there's an actual calculation for this. So you can use Boyle's law to calculate the volume of a gas following a pressure change, or the new pressure of a gas following a volume change, as long as the temperature and the gas remain the same. So you have to have those constant variables in order for this equation to be applicable. And the equation is P1V1 equals P2V2, where P1 is pressure 1, or what we call initial pressure, and V1 is volume 1, or initial volume, and P2 is pressure 2, or final pressure, and V2 is volume 2, or final volume. So let me show you an example of this. So if you're given a question like this to calculate the pressure of a gas that was initially at 765 mmHgs and 1.78 liters and later compressed to 1.25 liters, then you can use this equation. Now let me show you something here. So when I read these problems, because essentially we're going to talk about these 5 laws, right? And so by the end, it's never going to tell you this is Boyle's law or this is Charles' law. You have to be able to identify it based on the variables that you're given. So what I would do is I would say, okay, I have 700, you have a gas that was initially 765 millimeters Hg. Well, mmHg is a pressure unit, so I would immediately call this P1 because they told me it was the initial pressure. And 1.78 liters, that's my initial volume. So I said I have a V1. And later compressed to 1.25 liters. So I now have a V2. So I know the variables that I'm working with are pressure, volume, and volume. And it wants me to calculate a new pressure a P2. So I know I must be working with Boyle's law based on the data set that I've been given. I know I'm going to plug into this equation. So I'm going to write out all my variables. I highly recommend doing this because you're going to have to plug into this equation, which is going to need to be rearranged. Now, if you're not strong in algebra, let me remind you how to rearrange this equation. So if I have P1 V1 equals P2 V2, and what I need to isolate, remember, is my P2. So I'm going to take this V2 and divide it. So I can isolate the P2 on the right-hand side of the equation. So I'm going to end up with P1 V1 over V2 equals P2. That's how you isolate. So then I can just plug my variables in directly. You might want a calculator here. So this unit, it'll be helpful to have a calculator. I know we haven't really needed to use that in a while. And if I rearrange this and I plug in my variables, I get 1089.36, or now we're talking sig figs again because we're doing math. I only have 3 sig figs max, 1.09 times 10 to the 3 mmHgs. And remember units. Notice I have units on every single part of this equation. Always put units in and always remember sig figs. Okay. So now we're going to do a U-try. So this is where you're going to use that piece of paper, and as soon as I switch to the next slide, I'll have the answer, but please give it a try. Okay. So here are the answers. Now on this one, I highlighted everything for you. So a cylinder equipped with a movable piston has an applied pressure of 4 atm and a volume of 6 liters. What is the volume of the cylinder if the applied pressure is decreased to 1 atm? So I have a cylinder where I'm changing the volume. So my initial pressure is 4.0 atm, and I wrote that in. My initial volume is 6.0 liters, V1. The volume of this, what is the new volume of the cylinder if the applied pressure is decreased to 1.0 atm, my new P2. So I have to rearrange this equation. This time I'm isolating V2 though, not P2. So I rearrange in the exact same way. So V2 is alone on the right side of the equation, and I replug these numbers in. Again, notice that there are units on every single step of this, where my new V2 works out to 24.0 liters. Okay. Now, we just learned Boyle's law. Now we're going to look at Charles' law. So Boyle's law looked at volume and pressure. I'll go back here. Pressure and volume. Now Charles' law is going to look at volume and temperature. So we're comparing two new variables here. So the volume of a gas and its Kelvin temperature are directly proportional. Directly proportional means that as one goes up, so will the other. If one goes down, so will the other. So they work in the exact same way. If the temperature of the gas sample is doubled, then the volume is going to double as well. Okay, so anything that one does, the other will follow with. So let's look at this. If I am looking at the volume of a balloon, if everything else remains constant, meaning the quantity of gas remains constant and the shape that the balloon is in, if I apply heat, if I increase the temperature, then the volume is going to increase in this balloon. Whereas if I apply cold, then the temperature decreases, then the volume will also decrease. Okay, so let's look at the equation for Charles' law. So Charles' law has this equation. So you can use Charles' law to calculate the volume of a gas following a temperature change, or the new temperature of a gas following a volume change. And this, as long as the pressure and the quantity of gas remain the same. Now look what's different about this equation. Instead of multiplying V1 by T1, we're actually dividing V1 by T1 and setting that equal to V2 over T2. Where again, V1 is the initial volume, T1 is the initial temperature, V2 is the final volume, and T2 is the final temperature. So let's look at an example here. So we have a 2.37 liter sample of a gas at 298 K. That is then heated to 354 K with no change in pressure. So what is the final volume of the gas? So I'm going to go back and again identify my variables. So we have a gas that has a 2.37 or a 2.37 liter sample. So that's going to be volume 1. And it's at 298 K. That's going to be T1. That is then heated to 354 K. That's T2 with no change in pressure. What is the final volume? And we are searching for V2. So now what we have to do is look at how this needs to be rearranged to solve for V2. So in this case, I rewrote it out so that they look more like fractions. I have V1 over T1 is equal to V2 over T2. And in this case, we cross multiply. So we're going to rewrite this equation as V1 times T2 equals T1 times V2. So it'll look more similar to that last equation. And from here, you should be able to isolate algebraically the same way you did the Boyle's law equation. And in this case, V2 is what you're searching for. That's here. So we will take our T1 and divide it by the other side. So you end up with V1 T2 over T1 is equal to V2. And then, of course, you can plug your variables in, reminding yourself to put those units in. And you'll end up with something that has the same amount of sig figs as your initial equation. And in this case, it's about 2.82 liters. Okay, so we're going to do a U-try. Again, put this down on a piece of paper. You'll need to submit. A sample of gas has a volume of 2.80 liters at an unknown temperature. What is the sample? When the sample is submerged in ice water at T equals 0 degrees Celsius, its volume decreases to 2.75 liters. What is the initial temperature in degrees Kelvin? Notice the unit change. Notice the unit change here. It gives you an answer in Celsius, but wants, or it gives you content in Celsius, but wants an answer in Kelvin. You will need to reference your sheet, but I will tell you that anything to get from Celsius to Kelvin, you're going to add plus 273. So if you have an answer in Celsius, you add 273. That will give you an answer in kelvins. Okay, go ahead and give this a try and go to the next slide when you're ready. So here are the answers to this one. So a sample of gas has a volume of 2.80 liters at an unknown temperature. So sample of gas has volume 1 at an unknown temperature. So T1 equals question mark. When a sample is submerged in ice water at T equals 0, that's T2 degrees Celsius, it is that the volume then decreases to 2.75 liters, volume 2. So we know we are looking for T1. So I can rearrange this equation. V1 T2 over V2 is set equal to T1. I can plug in each of these variables. Again, remembering units. Before I do this, though, I want to make sure I convert from my 0 degrees Celsius to Kelvin. And because this is 0, I can easily add the 273 and get 273 Kelvin and plug that in and get an answer in degrees Kelvin like it asked me to, and I get 297 Kelvin. Okay, guys, that's it for today. Let me know if you have any questions, and we'll be going over this in class as well. Thanks.